Picture this, a startup migrates everything to a single S3 bucket on day one of their cloud journey. They pick the cheapest tier, click through the defaults, ship the product. 18 months later, they get a security questionnaire from an enterprise customer asking who is responsible for patching the operating system. Nobody on the team can answer. They open a support ticket with the cloud provider and get back 2 words: not us. That is the moment the founder realizes the cloud did not buy them out of security work. It just moved the line. Today we draw that line. Architecture models, deployment styles, and the security implications of every choice you make above and below the hypervisor. This is Objective 3.1, and the exam is going to ask you to identify the model, identify the responsibility, and identify the risk. Let's get to it. Start with the concept the exam loves more than any other in this domain: the shared responsibility model. There are 3 flavors of cloud you have to know, and the only thing that changes between them is where the line sits between the provider and you. IaaS, infrastructure as a service, is the rawest. The provider gives you hardware, hypervisor, networking, storage. You bring the operating system, the runtime, the middleware, the application, and the data. Think AWS EC2, Azure VMs, Google Compute Engine. You patch Linux, you patch Windows. The cloud provider does not. PaaS, platform as a service, pushes the line up. The provider hands you a managed platform. Your job shrinks to 2 things: the application code and the data. Heroku, Elastic Beanstalk, Google App Engine. You ship a tarball, the platform runs it. They patch the runtime, they patch the operating system, they keep the load balancer alive. SaaS is the top of the stack. You are renting the entire application. Office 365, Salesforce, Google Workspace. Your responsibility shrinks to 2 things and only 2 things: your data and who has access to it. That is it. Here's the part that trips people up. The cloud provider is never responsible for your data classification, your access policies, or your encryption key management. Never. Even on SaaS, where they patch literally everything, if you give a contractor admin rights to your tenant and they walk off with the customer list, that is on you. The exam will hand you a scenario that says, quote, "The cloud provider lost a hard drive containing customer data," end quote, and ask whether the breach is the provider's fault or yours. The answer is almost always you. The provider lost a piece of hardware. The data on that hardware was your responsibility to encrypt before it ever touched their disk. Rank the 3. SaaS shifts the most risk to the provider. IaaS shifts the least. Visibility goes the opposite direction. You see the most in IaaS and the least in SaaS. Hybrid cloud is the in-between. On-prem plus 1 or more cloud environments stitched together. The pitch is the best of both worlds. The reality is 2 environments, 2 policies, 2 sets of identity, and a data path between them that nobody fully owns. The fix is unified identity. Azure AD Hybrid Sync is the textbook example, and consistent encryption end-to-end. If your on-prem encrypts at AES 256 and your cloud copy lives in clear text on a developer laptop, the hybrid posture is only as strong as the laptop. Then there is the third-party problem. Vendor lock-in is when you are so embedded in a single provider that switching is not technically feasible. That sounds like a procurement issue until the provider gets compromised and your only option is to ride it out. Supply chain risk is worse. SolarWinds 2020, one poisoned update propagated to roughly 18,000 customers. The lesson: your vendor's vendor is also your vendor. Vet them. SOC 2 Type 2 reports, pen test summaries, a real SLA. If the answer to "do you have a recent third-party audit" is, quote, "let me get back to you," end quote, you already know. Infrastructure as code, IAC. Stop clicking around in the cloud console. Define infrastructure in declarative files, check them into Git, deploy with a pipeline. Terraform, multi-cloud. CloudFormation, AWS only. Bicep, Azure only. Done well, you get reproducible environments, audit trails, and rollback. Done badly, you get 4 risks that the exam will hand you in scenario form. 1. Misconfigured templates that deploy the same insecure config across every region simultaneously. 1 bug, blast radius equals everything. 2. Secrets hard-coded in the file. An API key in a Terraform module checked into a public repo is a credential leak the moment the commit lands. 3. Uncontrolled repos. Treat IAC repos like production secrets. 4. Drift. Somebody SSHs in and changes a security group manually. The template no longer matches reality. Drift detection, Terraform plan, AWS config is how you catch it. Version control is not optional. It is the primary mitigation. Serverless. FaaS. Function as a service. The provider runs your code in short-lived ephemeral containers. No OS to patch. No server to harden. AWS Lambda, Azure Functions, Google Cloud Functions. The marketing pitch is, you have nothing to defend. Mostly true. Your OS attack surface really does shrink. What you traded for it is 2 new problems. Function injection, same as application layer injection in any traditional app, except now your function might pull from an event source you do not fully control, and the input gets parsed into something dangerous. And over-permissive IAM roles. 9 times out of 10 the engineer attached an admin role to the function because, quote, it is faster than figuring out the right policy, end quote. Compromise the function, you compromise the role. Audit logging is also harder because the execution windows are short, cold starts are weird, and the forensic trail is fragmented. Microservices. The opposite of a monolith. Instead of one big application, you ship dozens of small, loosely coupled services that each do one job and talk to each other over APIs or message queues. Kafka, RabbitMQ, gRPC. Usually containerized. Usually orchestrated by Kubernetes. The security story changes shape. Every internal call is now an API call. Every API call is a new attack surface. Service-to-service authentication is required, not optional required. And the textbook answer is mutual TLS, mTLS, usually managed by a service mesh like Istio. The blast radius of any single compromise is smaller. That is the win, but lateral movement between services is a real path. If you have ever debugged a TLS handshake at 3 a.m., you know how easy it is to ship a service with a misconfigured cert and not notice until something fails open. Now, network infrastructure models. The most secure option on paper is the air gap. The network is physically disconnected from the internet and every external network. Classified government systems. Nuclear plant control. Critical SCADA. Data transfer happens by sneakernet, USB, optical disk, hand carry. The exam wants you to know it exists and to know that it has been defeated. Air gap bridging attacks are real. AirHopper exfiltrates data over FM radio frequencies from a video card. Mosquito does it through speakers and microphones as ultrasound. The air gap is the highest level of security available, and it still is not absolute. Logical segmentation is the cheaper, more practical cousin. VLANs at layer 2. Subnets at layer 3 with ACLs and firewall rules between them. You share physical infrastructure but separate traffic logically. It is not as strong as physical isolation, but for the vast majority of corporate environments, it is the right answer. Then there is SDN, software-defined networking. The control plane and the data plane get split. A central controller decides routing. Switches just forward. The benefit is enormous flexibility. Programmable networks, API-driven changes, dynamic policies. The risk is a single point of failure that did not exist in the old hardware-only world. Compromise the SDN controller and you control the entire network. The SDN controller is the highest value target on a software-defined network. Treat it that way. On-prem versus cloud is the procurement meets security comparison. On-prem is full control, full responsibility, capital expense, and limited by whatever hardware you own. Cloud is shared control, shared responsibility, operational expense, and elastic. Patching is fully yours on-prem. In cloud, it depends on which service model you picked. Centralized versus decentralized architecture is a different cut. Centralized, one SIEM, one identity provider, one data center, is easier to manage and easier to monitor, and it is also a single point of failure. Decentralized, distributed mesh, blockchain, edge computing, is more resilient and harder to monitor. The exam asks you to pick the right trade-off for the scenario. There is no universally correct answer. Containers and virtualization. People conflate them, the exam will not. A virtual machine has its own kernel running on top of a hypervisor. A container shares the host kernel and isolates processes inside namespaces and C groups. VMS give you stronger isolation. Containers give you portability and density. Docker is the runtime everybody knows. Kubernetes, K8s, orchestrates containers at scale. The container security risks the exam wants are predictable. Vulnerable base images pulled from public registries. Scan with Trivy or Claire. Registry compromise. Restrict push access. Sign images. Prefer private registries. Containers running as root. Do not ever use pod security policies and run as non-root. And container breakout, where the attacker escapes the namespace and lands on the host. Patch the runtime. Patch the kernel. Isolate workloads. Virtualization. Hypervisors come in two types. Type 1 is bare metal, VMware ESXi, Microsoft Hyper-V XN, running directly on hardware with no host OS underneath. Type 2, VirtualBox, VMware Workstation, runs on top of an existing operating system. Type 1 is more secure, smaller attack surface, no host OS to compromise. The catastrophic risk on either type is VM escape. An attacker breaks out of a guest VM and lands on the hypervisor or another guest. Critical, high severity, rare but devastating. Snapshots, point-in-time copies of a VM, are useful for recovery and for malware sandbox analysis. Take the snapshot, infect the VM, study the malware, revert. They are also a backup adjacent control, not a backup itself. IoT and industrial systems. IoT devices, sensors, cameras, smart appliances, industrial monitors, wearables share the same four problems. Default credentials that nobody changes. Patching that ranges from rare to impossible. Protocols that often skip encryption and authentication entirely. ZigBee, Z-Wave, MQTT are the usual suspects. And no traditional endpoint security available, because most of these devices cannot run an EDR agent. The scale of IoT is the multiplier. Millions of devices, weak by default, exposed to the internet by default. Then there is industrial. OT, operational technology, controls physical processes. ICS, industrial control systems, is the broad umbrella. SCADA, supervisory control and data acquisition, supervises distributed systems like power grids, water treatment, and pipelines. RTOS, real-time operating systems, run medical devices and vehicles where deterministic timing is the safety property. Embedded systems are single-purpose devices with fixed firmware, printers, routers, vehicle ECUs. The big difference between IT security and OT security: when OT fails, people can die. Stuxnet 2010, nation-state malware that targeted Iranian nuclear centrifuges via Siemens PLCs. It physically destroyed equipment by spinning rotors past their tolerance while reporting normal status to operators. That is the canonical ICS attack, and the exam will name it. Legacy OT often cannot be patched without operational downtime, which is why operational continuity beats patching cadence in those environments. The preferred control is air gap. When that is not possible, use a data diode, a unidirectional gateway that lets data out for monitoring but physically prevents anything coming back in. High availability rounds out the architecture menu. Load balancing distributes traffic across multiple servers, so no single server is the bottleneck or the single point of failure. Clustering groups servers that share state so that one node can fail, and the others keep going without interruption. Redundancy is the hardware layer of the same idea. Dual power supplies, dual NICs, RAID storage. We will get deeper into HA 3.4 when we talk recovery. For now, recognize the terms and know they all exist to eliminate single points of failure. Quick scenario walkthrough, because the exam will hand you these in plain English and expect you to translate. Scenario 1, quote, the company stores customer data in Salesforce, end quote. Service model is SaaS. The provider patches the application and the underlying stack. Your responsibilities are exactly two: the data and who has access. The encryption keys for any field level encryption you turn on are still your problem. Scenario 2, quote, the team deploys their workload to AWS Lambda, end quote. Service model is serverless FaaS. The provider runs the runtime. Your responsibilities are the function code, the trigger configuration, and the IAM role attached to the function. Scenario 3, quote, engineering uses Terraform to deploy VMs in Azure, end quote. Service model is IaaS. You patch the operating system on those VMs. The Terraform code itself is IAC and lives in version control with secret scanning. 3 different scenarios, 3 different responsibility lines, 3 different control sets. The exam will expect you to draw the line correctly every time. One more nuance the exam likes. Storage architectures inherit the security properties of the deployment model that hosts them. Object storage in IaaS, AWS S3, Azure Blob, is your responsibility to encrypt with server-side encryption and your responsibility to gate with bucket policy. SaaS storage, SharePoint Online, Google Drive, is the provider's responsibility to operate, but yours to configure access correctly. The classic mistake is assuming that because the provider runs the storage, the access controls are also handled. They are not. The default sharing setting on a SaaS file storage product is one of the top causes of accidental public exposure. Audit it. Action checklist. 1. For every cloud workload, write down which service model you are using, then write down what your responsibility is in that model. If you cannot say in one sentence who patches the OS, you do not understand the deployment. 2. Never trust a cloud provider with key management or access policy. Those are yours, regardless of model. 3. Put IAC in version control, scan for secrets before commit, and detect drift continuously. 4. For serverless, scope the IAM role to exactly what the function needs and nothing more. 5. For microservices, mTLS between every service, no exceptions. 6. Pick logical segmentation as the default and air gap only when the workload genuinely justifies it. 7. Type 1 hypervisor over type 2 whenever possible, and patch the hypervisor like it is the front door. 8. For IoT and OT, change default credentials, isolate the segment, accept that patching may not happen, and compensate with monitoring. 9. Name Stuxnet when the exam asks for an ICS attack. Name SolarWinds when it asks for a supply chain attack. 10. The higher you go up the cloud stack, the less you see and the more you trust the provider. Choose accordingly. Next up, Objective 3.2, Security Principles for Enterprise Infrastructure. We have just talked about where workloads live. Next, we talk about what sits in front of them: firewalls, proxies, load balancers, jump servers, and the zones we drop them into. We will start with a real DMZ built badly and walk through the appliances in the order an attacker would meet them. See you in 3.2.